Welcome to the last video where I'm going to be explaining flattening the curve and what that means. First, let's draw out the graph. So you've probably all seen something like this going around, and probably better than how I've drawn it. But this is flattening the curve, where we're shown two curves of how the number of people grows with respect to time, as we've all done for the past few videos. One of them, it grows very fast, right over here. It grows up, and it goes down very fast as well. The other one takes some time to grow, and it flattens out very slowly. This dotted line is the healthcare capacity, and obviously the one that grows very fast passes the healthcare capacity, so at these times you'll get a lot of people who are infected, but there's no hospitals to go to because the hospitals are completely full. And for the lower graph, everyone's going to get a hospital to go to. This is the ideal situation. You're not going to have the case of hospitals overflowing with patients. What we want to do is we want to flatten the curve by making this steeper one look more like this shorter one over here. But before we get to that, we first have to get the curve, right? Our past two curves don't look anything like this. They look like these: the exponential curve and the logistic curve. They don't look like this curve yet. Our fault for the exponential curve is that we assumed the infection rate would keep growing forever. We never took into account the population cap. For logistic curve, we solved that problem of the population cap, but we assumed that nobody recovered from the disease. And that's the biggest fault here. People do recover for the disease. For example, for the coronavirus, some countries have death rates less than 1%. Other countries have it at 10%, say. But either case, it's not 100%. It's much better than that. So we have some hope, right, for a better equation. And this is where we get into something called the SIR model. So we're going to have three variables because one variable is not enough anymore because we have to account for people recovering. We have S is equal to susceptible. We're going to have I is infected and R is recovered. And for all of these graphs, we've been looking only at I, infected, whether for exponential or for logistic or what we're going to look at right now. It's all the infected number of people as a function of time. So what we're assuming in this case is a little bit more complex. We have the number of susceptible people, which is healthy. This decreases at a rate proportional to that gets bigger if S is bigger, and also gets bigger if I is bigger. So if you have a lot of infected people, you're obviously going to transmit more infections. If you have a lot of people that are susceptible to be infected, then you're also going to have a lot of change in susceptible people. So we're going to have three differentials here, actually. We're going to have ds over dt, which is what I was just talking about. And we're going to have di over dt. This is the change in number of infected people. And we have dr over dt. This is the change in recover people. Another assumption we're making is that once you recover, you get immunity from the disease. You're never going to get it again. In some models, R stands for removed, because some people, they don't recover, but they pass away and they don't transmit the disease anymore, and you have to account for that in your model. So dr over dt is going to be some fraction of the infected people. Let's say ds over dt is some constant, and we want, for over here, we want a value that gets big when S is big and gets big when I gets big. And the simplest thing you might think of is just to multiply them. dr over dt is only proportional to the number of infected people. Let's say, for the simplest assumption, we're just going to say a certain fraction of the infected people recovers. For example, maybe after 20 days, the average person recovers. So we're going to have a constant times the number of infected people. We're going to have constant 3 times, let's make it constant 2 actually, times the number of infected people. Also we know that ds over dt, S is getting smaller, so we actually need a negative sign here. And dr over dt is getting bigger. Now di over dt, you're going to have some people getting infected, C1 times Si. These are the number of people going from susceptible to infected, and you have to subtract C2 times I. And this is the number of people that are recovering. So these are our three models. Unfortunately for this one, we can't solve these by hand. At least I don't know of a method to solve these by hand. So we would just use a calculator to graph it. And when you do graph it, you do get this curve over here. This curve that looks like this. So that's great. Using this model, we get the bell-shaped looking curve over here. And yeah, I don't know if that's how experts got it, actually. They probably use some more advanced techniques. But now we get this curve over here, and these constants are constants telling you how fast people get infected and how fast people start recovering. Constant 1 is something we want smaller. We don't want people to get infected quickly, and that's why we have something called social distancing. If people are staying at home, well, you're going to have less human contact, so not a lot of people are going to get infected, and constant 1 is going to be pretty small. Also, constant 2 is the number of people that are recovering. So that's why we have all our doctors and nurses still working. So constant 2 can be bigger. We're saving people's lives more quickly. Also, if the population in general is healthier, then constant 2 is going to be bigger, because for this disease, people can recover by themselves as well. So that's flattening the curve, and yeah, that's basically it. We want people to stay away from each other, and we don't want to exceed our healthcare capacity. So that's all I have for you. Thanks for watching, and I hope you learned something new.